All right, guys, we're back today, and I'm going to go over some specific gas laws. You're going to be asked to do some calculations on these, so be sure as we go through here you get the formulas. So the gas laws that I'm going to go over are the relationships that we find between pressure, temperature, volume, and the amount of gas. And most of these gas laws are fairly common sense to you guys. So the first gas law that we're going to look at is Boyle's law, and it is a pressure-volume relationship. If the pressure of a gas is increased, it's like we take and we squish those molecules closer together, the volume goes down. So it's actually an inverse relationship. As one value goes up, the other value goes down, and vice versa. So it's an inverse relationship. If we actually multiply these two variables together, it equals a constant. So any pressure volume combination here equals a constant. We're going to use that, though, to our advantage to solve a problem, because if we kind of maintain that same system, if it's equal to a constant, then we can change the pressure or the volume and still have that same constant. So our formula that we're going to use to work Boyle's law is pressure times volume equals pressure times volume. Now this relationship is only valid if we do not change the temperature of the system, or as long as we don't add or remove the amount of gas. So here are our variables. If we're working with these two, the other variables have to remain unchanged or this gas law doesn't work. So pressure times volume equals pressure times volume. The only thing that you're going to run into sometimes is that pressures and volumes are not always given to you in the same units. So you need to pay attention for that. If pressure is given to you in atmospheres here, you need to be sure you're using the same unit of atmospheres on this side. If volume is given to you in liters, you need to be sure that volume here is also in liters. So we have to double check our units and convert. So if one was liters, one was milliliters, we need to make them the same unit. Now I don't care which one you go to, if you change milliliters to liters or vice versa, whatever works for you. So remember from the previous video, we had lots of different units for pressure. So we could have atmospheres, we could have kilopascals, we could have millimeters of mercury. So lots of different pressure units. If the pressure units don't match, set it up like a little dimensional analysis problem to get to the unit that you want. So if it's, and on that other video, I also gave you lots of what it was equal to, and I think I had 1 atmosphere equals this, 1 atmosphere equals that. That can be your known factor. So if the problem says that you have 730 millimeters of mercury, and to work the problem you need it in atmospheres, put your known value for how many millimeters of mercury is in 1 atmosphere here. So you're going to have millimeters and atmosphere here. You're going to cancel your units, do your math, and you're going to have your answer to convert your units. If you need to go from milliliters to liters, remember liters would go right there in the middle. So remember moving the decimal. If you had milliliters and you needed liters, we would have to move the decimal 1, 2, 3 places to the left. And vice versa, if we had liters and we wanted to put it in millimeters, we would need to move the decimal 1, 2, 3 places to the right. So don't forget, and don't forget to check on those particular things to be sure that your units match. So other than that though, really just decide if your problem, you know, if you're putting the one that gives you both pieces of information about, doesn't really matter. Just plug one in. Call one the before and one the after. Plug in your variables and solve for X. I will make a video where I kind of go through some practice problems with you, and then you'll have an assignment where you actually do your own practice problems. The next gas law is Charles's law, and this is our volume temperature relationship. So if the temperature of a gas is increased, we expect those molecules to start moving around faster, and as they bump and collide more, they actually start to fill up more space. They increase their volume. And just like the other one, we expect the other two variables to remain unchanged. So if we're changing volume and temperature, we are not allowed to change the amount of gas or the pressure that the gas is held at. So a volume temperature relationship. So this relationship is proportional. If one goes up, the other one goes up as well. And these would both be equal to a constant. So same idea as before. If it's equal to a constant, then we can make a change in the system. And now we have V over T equals V over T. So one side could be like before a change and after a particular change. So if we needed a gas to fit into a very small container, we could figure out how we need to affect the temperature in order to make it fit into that smaller container. There is an issue with this particular problem, and that is the fact that temperature must be in Kelvin. So Kelvin is 273 added to your Celsius temperature. And that's where these practice problems are going to kind of get you. You're going to think you've done them correctly, but you're going to have plugged in your Celsius temperature and you didn't change it to Kelvin, so you're going to end up missing the problem. So be sure that temperatures are in Kelvin. They have to be in Kelvin for this problem. Volumes, it doesn't matter as long as the unit is the same. So if you're working with milliliters on one, be sure it's milliliters on the other. And same thing if it was liters, be sure they're matching units. So for this one, it's essentially a cross, multiply, and divide. Put an X in for your unknown factor. Do the cross multiply thing. And then, so you're going to have this T and this V over here equals this V and this T over here with an X for your unknown. And then solve for X. So cross multiply and divide. Gay-Lussac's law, pressure and temperature relationship. So if I increase the temperature of the gas, I also increase its pressure, which kind of makes sense because it's going to be colliding more with the walls of the container. Since we're working with these, the two factors that have to remain the same are the volume and the amount of gas. So we have to keep those other factors the same. So this becomes exactly the same as before. Pressure over temperature equals pressure over temperature. Again, Kelvin, the temperature must be in Kelvin for this one, just like here. So this is a direct relationship. Increase the temperature, increase the pressure, decrease and decrease. Pressure, again, in units as long as it's the same. So we can actually put all these gas laws together into something called the combined gas law. And I actually find it easier to remember the combined gas law and just scratch off the part I don't need if I don't need part of it. Combined gas law just combines all of them. So pressure times volume over temperature would have to be equal to pressure times volume over temperature. So we've literally just thrown all of these gas laws together. Again, we have to maintain the other variable and not change it. So we are dealing with a constant amount of gas if we're working with this. And as you can already imagine that I'm going to say, if pressure is in 1 unit here, it must be a matching unit. Same thing with volume. And temperature must be in Kelvin for this to work. The last gas law that I've got for you here is Avogadro's principle. And this is where we're dealing with the amount of gas. And he says that if you have equal volumes of gas, so let's say I have a volume like this, say a balloon volume like this, and another balloon volume like this, equal volumes, they would contain equal numbers of particles. So this one's filled with carbon dioxide, this one's filled with helium. If they are the same size, the same volume, they would have the same number of particles in them if our other variables remain the same. So they're held at the same temperature and they're held at the same pressure. So that's Avogadro's principle. Remember, gases are very, very small in comparison to the amount of room they take up. They're widely spread apart particles that are moving. So it doesn't really matter if it's a bigger molecule like carbon dioxide or a smaller molecule like helium. Which brings us then to the ideal gas law. So the ideal gas law actually includes Avogadro's principle in it. And I'm not going to ask you to work any types of calculations with this since we're not at school, but it is PV equals nRT. So pressure times volume equals N. That has to do with the number of moles of gas. So we have to convert amount to moles. R is a constant, a number that you would have been given and asked to remember. The R value is different if you're using atmospheres for your pressure or if you're using like kilopascals, and then T for temperature in Kelvin. So we're not going to do any calculations with this, but we would have, and we would have done a lab where we would have actually experimentally figured out the value of R. We've got all these gas laws, and our gas laws work wonderful for ideal gases. So what's an ideal gas law? It follows all parts of that kinetic molecular theory that we went over before in all situations. So remember, they're perfectly elastic. There's no attraction between molecules, all of those things. So an ideal gas follows those things at every conceivable condition. There's no such thing as an ideal gas. Gases do act like an ideal gas most of the time, but when we really get to like crazy low temperatures, we cause those molecules to sort of vibrate less and less and less, and we can cause the gases to turn into a liquid. So we can violate then this whole ideal gas law because now we have some attraction between our particles. At very, very high pressures, we can do the same thing. We can force those molecules to get so close together through very high pressures that they might kind of stick together. So we don't have a thing that's an ideal gas. There's not an ideal gas. But most gases act like ideal gases most of the time. So we're able to use all of these particular gas laws.